The Fermi Paradox. The universe is vast, with billions of stars, countless planets, and unimaginable distances stretching across space. It seems almost certain that we are not alone. After all, if the universe is as old and expansive as we think, then intelligent civilization should be everywhere, right? Yet despite all the evidence that life is possible, we find ourselves alone in the cosmic void. This is the Fermi Paradox, a question that has puzzled scientists, philosophers, and anyone who's ever wondered if we're alone in the universe. The Fermi Paradox is a simple question. Where is everybody? If the universe is so big and so old, why haven't we found any signs of extraterrestrial life? Where are the aliens? This paradox is named after physicist Enrico Fermi, who famously posed the question in the 1950s. Fermi was part of a group of scientists discussing the probability of intelligent life in the universe. He calculated that given the number of stars and planets out there, the chances of intelligent life existing were extremely high. Yet, despite this, no one had any solid proof that such life existed, and the universe seemed eerily quiet. To understand why the Fermi Paradox is so puzzling, it helps to consider a few factors. First, the sheer number of stars and planets in the universe. The Milky Way alone is home to about 100 billion stars, many of which are orbited by planets that could potentially support life. The number of galaxies is even more staggering, with estimates ranging in the trillions. If even a small fraction of these planets host life, that means there could be millions of civilizations out there. So why haven't we heard from them? One possible explanation is that alien civilizations are simply too far away. The vast distances between stars make interstellar communication incredibly slow. The fastest signals we can send, traveling at the speed of light, would take years, centuries, or even millennia to reach the nearest stars. So, if there are alien civilizations out there, their signals might not have reached us yet, or vice versa. Maybe we're just too far apart, and by the time a signal reaches us, both civilizations will have moved on, leaving only silence behind. Another possibility is that intelligent civilizations are incredibly rare. It's possible that life itself is common throughout the universe, but intelligence might be an exceedingly rare phenomenon. After all, it took Earth billions of years to evolve a species capable of advanced technology and space travel. Perhaps most planets simply don't produce intelligent life, and instead, life on those planets remains stuck in simpler biological forms. If intelligent life is as rare as it seems, we might just be one of the few lucky planets to have developed it. Perhaps the most disturbing explanation is that civilizations tend to self-destruct. Known as the Great Filter Hypothesis, this idea suggests that the path from primitive life to a fully developed spacefaring civilization is fraught with dangers. These dangers might include nuclear war, environmental collapse, or the uncontrolled growth of artificial intelligence. In this scenario, intelligent civilizations inevitably destroy themselves before they can reach a level of development that allows for interstellar travel or communication. If this is true, it could mean that we are heading toward our own extinction, and we might be the last species to ever get the chance to explore the cosmos. Another unsettling theory is that advanced civilizations are out there, but they're simply choosing not to contact us. This is part of the dark forest hypothesis, which suggests that civilizations in the universe may be deliberately keeping their presence hidden. The idea is that the universe is like a dark forest, where every civilization is a hunter trying to survive. In such an environment, revealing one's existence could be a deadly mistake, as it might attract the attention of more advanced, potentially hostile civilizations. So to stay safe, civilizations may remain silent, avoiding any signals or attempts at communication. all while silently observing the universe from the shadows. Some have speculated that the reason we haven't found extraterrestrial life is that we're simply not looking in the right way. Perhaps alien civilizations communicate in ways that we cannot detect. Our search for alien signals is primarily focused on electromagnetic radiation, such as radio waves, but there could be entirely different forms of communication we are missing. For instance, aliens might use quantum signals, gravitational waves, or other forms of technology that are beyond our current understanding. It's possible that alien civilizations have been trying to reach us for centuries, but we just haven't developed the technology to recognize their signals. In some ways, the Fermi Paradox may also be a question of human hubris. Are we expecting extraterrestrial civilizations to look and think like us? If alien life exists, it might not even resemble anything we can imagine. The diversity of life on Earth, from simple bacteria to complex human beings, suggests that life could take on a variety of forms. An alien civilization might think, act, or even communicate in ways that are so fundamentally different from us that we wouldn't recognize it as intelligent life at all. Finally, the simplest explanation could be the most unsettling one. We are alone. It's possible that the universe is, in fact, empty of intelligent life, and that we are the only intelligent species in existence. This would mean that Earth and humanity are incredibly unique, and there may never be any other civilization to share our journey with. This idea challenges our assumptions about our place in the cosmos, but it's one of the possibilities that must be considered. The Fermi Paradox doesn't have an easy answer. The truth might lie somewhere in the vast range of possibilities, or we may never find out. But the fact remains, despite the staggering number of stars, planets, and galaxies out there, the universe remains eerily quiet. And until we find an answer, we'll continue to ask the same question: where is everybody? The Dark Matter Paradox. The dark matter paradox arises from the fact that we know this mysterious substance exists, but we have no direct evidence of it. We can observe its effects on visible matter, like galaxies and galaxy clusters, but we've never actually seen dark matter. Despite this, it seems to make up about 27% of the universe's total mass and energy, more than 5 times the amount of ordinary matter that we can see and detect. So, how can we know it's there, but still have no idea what it actually is? The story of dark matter begins with astronomical observations that simply didn't add up. When scientists looked at galaxies, they noticed something strange. Galaxies rotate at speeds that are too fast for their visible mass. According to Newton's laws of motion, galaxies should be spinning so fast that the stars on the outer edges would be flung into space. Yet, they aren't. Instead, they stay firmly bound to their galaxies, indicating that there is something invisible, something we can't see, providing additional mass and gravitational pull. This unseen substance was given the name dark matter. At first, it seemed like a simple solution. The laws of gravity were correct, but perhaps there was some mistake in the way we were measuring the mass of galaxies. But after more research, it became clear that this mysterious force wasn't just keeping galaxies intact. It was playing a crucial role in the very structure of the universe. When scientists looked at clusters of galaxies, they found that the gravitational pull between galaxies was too strong to be explained by visible matter alone. If dark matter didn't exist, the galaxies would not be able to stay together, and the universe as we know it would collapse. Dark matter is crucial for the formation of galaxies as well. Computer simulations that model the evolution of the universe show that dark matter played an essential role in clumping together gas and dust. providing the gravitational scaffolding necessary for the formation of stars and galaxies. Without dark matter, the universe would look much different, and galaxies might never have formed the way they have. In fact, dark matter is thought to have shaped the entire cosmic structure we see today. But while dark matter's effects are undeniable, the paradox is that we've never actually detected dark matter directly. Despite decades of searching, we haven't found any particles or radiation that could be identified as dark matter. We know it exists because of its gravitational effects on ordinary matter, but we've never been able to observe it in any direct way. It's like a shadow in the cosmos, there but untouchable. It's called dark matter because it doesn't emit, absorb, or reflect light, making it invisible to our telescopes and other detection methods. But how can something be so fundamental to the universe's structure and yet remain so elusive? There are several possible explanations for what dark matter might be, but none of them have been confirmed. Some scientists think it could be made of particles called WIMPs, weakly interacting massive particles. WIMPs are hypothetical particles that are thought to be heavy and weakly interact with normal matter. If these particles exist, they could account for dark matter's mass, but despite intense experiments, no one has been able to detect WIMPs directly. Another theory suggests that dark matter could be made up of axions, extremely light particles that have been proposed as a potential dark matter candidate. Axions are also very difficult to detect, but if they exist, they could help explain some of the strange behavior observed in the universe. But again, no direct evidence has been found, and the search continues. Yet another possibility is that dark matter might not even be made of particles at all. Some theories suggest that dark matter could be an extra-dimensional effect or a modification of gravity. In other words, maybe the laws of physics as we know them don't fully explain the behavior of galaxies and clusters, and there's something about gravity that we don't yet understand. If this were the case, dark matter wouldn't be a substance at all, but rather a sign of incomplete knowledge about the nature of the universe. So why is this a paradox? It's because we know dark matter is there, but we can't see it. We can observe its effects on galaxies and cosmic structures, but we have no direct way of detecting it. It is one of the most profound examples of how the universe can behave in ways that defy our understanding of what is observable and what is not. It forces us to confront the limits of our scientific knowledge and challenges our ideas about what can be considered real in the cosmos. One explanation for why dark matter has been so hard to detect is that it might be spread out evenly throughout the universe, with no concentrations that we could easily point to. In this way, dark matter might exist all around us, constantly influencing the gravity of visible matter, but without any tangible form we can interact with or observe directly. This paradox isn't just a scientific mystery, it's a philosophical question as well. What does it mean to know something in the universe? Can something be real if we can't perceive it with our senses or instruments? The dark matter paradox forces us to reconsider how we measure and understand reality. It reminds us that the universe is far stranger and more complex than we could ever imagine. Ultimately, the dark matter paradox pushes us to expand our imagination. The universe is full of things we don't understand yet, and dark matter is just one example. As technology improves and our understanding of physics deepens, perhaps one day we'll discover what dark matter truly is. Until then, it remains a shadow, lurking in the background of our universe, a reminder of how much we still have to learn. The expansion paradox. The universe is expanding. That's a fact. But what if I told you that this simple, seemingly straightforward idea could lead us into a paradox? A paradox that challenges our very understanding of space, time, and the cosmos itself. This is the essence of the expansion paradox. When Edwin Hubble first observed galaxies receding from us in the 1920s, he made a groundbreaking discovery. The further a galaxy is from Earth, the faster it appears to be moving away. This phenomenon, now known as Hubble's law, suggested that the entire universe is expanding. The realization was nothing short of revolutionary. It shattered the prevailing notion of a static universe and set the stage for the Big Bang theory, which posits that all of space and time originated from a single point, then expanded outward over 13.8 billion years. The idea is simple: space itself is stretching. As it does, the galaxies within it move further apart. But here's where the paradox begins to form. If space is expanding, that means the distances between galaxies are increasing, right? But is that all there is to it? Is the universe just getting bigger, or is there something more at play here? Let's consider what happens if the universe is expanding at an accelerating rate. In 1998, scientists discovered that not only was the universe expanding, but it was doing so faster and faster, a phenomenon attributed to a mysterious force called dark energy. Dark energy is thought to account for roughly 68% of the universe's total energy content, and it is pushing galaxies apart. The paradox isn't just that the universe is expanding, it's that this expansion is accelerating in a way that contradicts our expectations. If galaxies are moving away from each other, the natural assumption is that everything should eventually spread out, getting farther and farther apart until the universe reaches a state of emptiness. But if the expansion continues accelerating indefinitely, then galaxies, no matter how far they get, will eventually become unreachable. This means that any future civilization, or any observer in the far future, could potentially see a universe where every galaxy is out of sight, leaving them in an empty, isolated void. This creates a separation not only in space, but in time as well. However, here's the kicker. If the universe is expanding at such an accelerating rate, how does it remain consistent with the observations we make today? The paradox lies in the fact that while we observe the universe expanding, we can't easily reconcile this observation with the conditions that must have existed at the beginning of the universe. If the universe was smaller at one point, how did this rate of acceleration suddenly emerge? And how can we predict where it will stop? Some scientists argue that the universe might eventually reach a point where the expansion stops, slowing down due to gravitational forces. If that happens, galaxies could start to come back together, leading to a future scenario known as the Big Crunch, where the universe would collapse in on itself. But if dark energy keeps pushing the expansion faster and faster, how does that scenario fit into the puzzle? It's as if the universe is constantly evolving toward two vastly different outcomes at the same time. The most unsettling part of the paradox is that the universe's expansion might mean the end of observation itself. If galaxies are indeed moving away from each other faster than the speed of light due to this accelerated expansion, it means that no matter how advanced our technology becomes, we may never be able to observe those distant galaxies again. As the space between them and us grows exponentially, their light will never reach us. We'll be stuck in an isolated pocket of the universe, unable to reach out or see beyond our cosmic horizon. Furthermore, if the universe is expanding forever, there's no telling what that means for the long-term future of matter itself. The fabric of space is stretching, and as it does, it could tear apart atoms, stars, and galaxies. If the acceleration keeps pushing things apart at an increasing rate, even fundamental forces and particles might eventually be torn apart in an event called the Big Rip. This would lead to the ultimate fate of the universe being a continual unraveling, leaving everything in an endless state of separation and isolation. The expansion paradox asks not just how the universe is expanding, but why it's expanding the way it is. We know the universe is getting larger, but we don't know why the rate of that expansion is changing or how it might end. The paradox is that we can observe the expansion happening, but we still can't fully grasp its long-term implications. Is the universe destined to keep stretching forever, leaving everything behind? Or will the forces within the universe eventually slow the expansion, leading to a different fate altogether? At its core, the expansion paradox is a paradox of knowledge and observation. We know the universe is expanding, but the deeper we probe into why and how this expansion happens, the more questions arise. The answers may exist out there, hiding in the cosmic fabric we've yet to understand, or maybe they'll remain forever beyond our reach. The universe is expanding, and with every inch of it, we're left to wonder, what will that expansion mean for us in the far distant future? And will we even be around to witness it? The Multiverse Paradox. The idea seems simple at first. Our universe might not be the only one. Maybe, beyond what we can see, there are countless other universes, each with its own version of reality. Some nearly identical to ours, others wildly different. It's a concept that has fascinated scientists, philosophers, and science fiction writers alike. But if this is true, it raises a troubling question, one that throws everything we think we know into uncertainty. If the multiverse exists, then everything that can possibly happen must happen somewhere. Every choice you didn't make, every road not taken, every version of history you can imagine, somewhere, in some other universe, all of it is real. There's a universe where you decided to stay home instead of going out. One where ancient Rome never fell. One where Earth never even formed. And one where you never existed at all. This is where the paradox begins. If infinite universes exist, then there must be versions of our world where the laws of physics work differently. Maybe in some, gravity is weaker. Maybe in others, time moves backward. If every possibility plays out somewhere, how can we define what's real? What does truth even mean in a system where every version of reality exists simultaneously? It gets even stranger. If infinite universes exist, then somewhere out there, there's a universe that looks exactly like ours. One where every moment, every atom, is identical to what we see here, except for a single tiny difference. Maybe in that universe, you're reading this script, but wearing a different shirt, or sitting in a different chair. Or maybe the difference is so small, so imperceptible, that you'd never know the difference at all. And then comes the biggest question of all. If infinite universes exist, why do we find ourselves in this one? Shouldn't we exist in one of the far stranger versions of reality? Maybe one where the laws of physics don't allow for intelligent life. Maybe one where the universe collapsed moments after it began. Yet here we are, in a universe that seems to be just right for our existence. Some scientists try to resolve this paradox with the anthropic principle, the idea that we observe this universe simply because it's one in which we could exist. If our universe weren't suited for life, we wouldn't be here to ask the question. But that answer feels unsatisfying. It doesn't explain why this universe exists the way it does. It just states the obvious. We exist because we exist. Then there's another possibility, one that might be even more unsettling. If infinite universes exist, then somewhere, right now, there's a universe where someone is experiencing your life exactly as you are. Your thoughts, your actions, your memories, all replicated elsewhere. Does that mean you are unique? Or just one of an infinite number of copies? If everything repeats endlessly across the multiverse, does individuality even exist? And if all possibilities exist, then what does that mean for free will? Every choice you make, every decision, plays out in different universes. There's a universe where you chose differently, where events unfolded in another way. So if every possibility happens, did you ever really have a choice at all? Or were all outcomes always inevitable, just waiting to be played out across infinite realities? The Multiverse Paradox leaves us in a strange position. If the multiverse is real, then our understanding of identity, reality, and existence itself begins to break down. We're left wondering, are we just one of countless variations? If so, what does that make us? And in the grand scheme of infinite possibilities, does our reality hold any special meaning at all? The Zeno's Universe Paradox. Imagine taking a step forward, a simple action, something you've done thousands of times. But what if, on a fundamental level, movement itself is an illusion? What if the universe is structured in such a way that motion should be impossible? This is the disturbing implication of Zeno's Universe Paradox. To understand it, imagine dividing the distance between you and your destination into halves. If you want to walk across a room, first you must cover half the distance, then half of what remains, then half again, and again. No matter how small the remaining distance gets, there will always be another half to travel. An infinite number of steps, each getting smaller, but never quite reaching zero. If you must complete an infinite number of tasks to reach any destination, how can motion ever be completed at all? This paradox, first proposed by the ancient Greek philosopher Zeno, seems absurd. We know motion happens, we see it everywhere. But the logic behind the paradox remains stubbornly difficult to dismiss. If space is infinitely divisible, then every movement should require traversing an infinite number of points. And yet, despite this, things move. For centuries, philosophers and mathematicians have debated the implications of Zeno's argument. Some claim it's purely a mathematical illusion, a misunderstanding of how infinite sequences work. Modern calculus, for example, provides a way to sum infinite series into finite results, effectively bypassing the paradox. Others argue that it points to something deeper, a fundamental issue with how we perceive space and time. But what happens if we apply this reasoning beyond simple movement? If the universe is infinitely divisible, then every point in space is made up of smaller and smaller pieces, stretching down forever. Does this mean the universe itself is made up of infinite layers of reality, each hidden beneath the one we can observe? And if time follows the same logic, does every moment contain an infinite number of smaller moments within it, meaning true change never actually occurs? Some interpretations of quantum mechanics suggest that, at an atomic level, space and time might not be infinitely divisible at all. Instead, they might come in discrete, indivisible units, like pixels on a screen. If this is true, then Zeno's paradox only seems confusing because we're assuming reality works differently than it actually does. But if space is infinitely divisible, then the paradox remains unsolved. Motion, change, and even the flow of time itself could all be illusions, tricks of perception that don't reflect the fundamental nature of the universe. In that case, the question isn't just how we move through space, it's whether we ever truly move at all. The perfect cosmological principle. Paradox. For a long time, scientists assumed that the universe should look roughly the same no matter where you are. This idea, known as the cosmological principle, suggests that on a large enough scale, no place in the universe is truly special. Every region of space should be statistically identical, with galaxies and matter spread out evenly in all directions. But some took this concept even further. The perfect cosmological principle argues that the universe should not only look the same in every direction, but also at every moment in time. It suggests that the universe has no preferred place or time. Its large-scale structure should be eternal and unchanging. If this were true, we would expect an even, uniform distribution of matter across space and time, with no major variations. Yet, when we look at the universe, that's not what we see. Instead of an endless, smooth expanse of evenly distributed matter, we find galaxies, clusters, and massive cosmic voids, structures spanning millions, even billions of light years. Some regions of space are densely packed with stars and galaxies, while others are nearly empty. The deeper we look, the more intricate and complex these structures become. This reality directly contradicts the idea of a perfectly uniform cosmos. So, what went wrong? If the universe was supposed to be uniform, why does it have such massive variations? One explanation is that the perfect cosmological principle simply isn't true. Modern cosmology suggests that the universe changes over time, expanding, evolving, and forming structures due to gravitational interactions. The early universe may have been more uniform, but tiny quantum fluctuations eventually grew into the massive structures we see today. However, some still argue that the paradox isn't fully resolved. If the universe is infinite and eternal, then why did it have an early state at all? Why did galaxies, clusters, and voids form in the first place if the universe was meant to be perfectly homogeneous? Could it be that our understanding of space and time itself is incomplete? Some alternative theories, like the steady-state theory, once tried to salvage the perfect cosmological principle by proposing that new matter continuously forms to keep the universe looking the same at all times. However, observations of cosmic expansion and background radiation eventually ruled this out. Yet, the paradox remains unsettling. If the universe was once nearly uniform, but later evolved into the highly structured cosmos we see today, does that mean there was an underlying force or law guiding its formation? Or is the large-scale structure of the universe simply a random outcome of chaotic physical processes? In the end, the perfect cosmological principle paradox challenges our most basic assumptions about the universe. If the cosmos isn't uniform across time and space, then what determines its structure? And if it is uniform in some deeper way, why do we see such enormous variations? The answer could reshape our entire understanding of the nature of reality. The Reversibility Paradox. A glass falls from a table and shatters into countless fragments. Spilled water spreads across the floor. The event is irreversible. No one has ever seen shattered glass spontaneously reassemble or spilled water gather itself back into a cup. Yet, if we look at the fundamental laws of physics, nothing forbids it. In fact, the equations that govern the movement of particles, from Newton's laws to quantum mechanics, are completely time reversible. They work just as well forward as they do backward. And yet, the universe doesn't behave that way. Time moves forward. Causes precede effects. People age, memories are formed, and entropy, disorder, always increases. This is the reversibility paradox. If the laws of physics don't distinguish between past and future, then why does reality? One possible answer lies in entropy, as described by the second law of thermodynamics. It states that the total entropy of a closed system always increases over time. A neat, ordered state naturally drifts into disorder, but disorder never spontaneously organizes itself. This is why broken glass doesn't fix itself, why heat spreads rather than concentrating, why the past feels different from the future. Entropy seems to be the arrow that forces time in one direction. But here's the problem. If entropy is the reason time moves forward, then why was the past ever in a low entropy state to begin with? The early universe, right after the Big Bang, was incredibly ordered. A tiny, dense, uniform state of energy. That's extremely unlikely. In fact, out of all possible ways the universe could have begun, a chaotic, high-entropy state would have been far more probable. So why did the universe start in such an unusual, low-entropy condition? One idea suggests that we might just be living in a rare statistical fluctuation, an accidental blip in an otherwise chaotic reality. Another proposes that entropy resets in cycles, meaning that the universe undergoes endless deaths and rebirths, each time resetting the direction of time. But even if these explanations make sense mathematically, they don't resolve the deep intuitive question: why is there an arrow of time at all? If a film of the universe played in reverse looked just as physically valid as the real thing, why do we only experience one version? What is it about consciousness, experience, and reality itself that prevents time from flowing both ways? Maybe time itself isn't what we think it is. Maybe our perception of time's flow is an illusion, a byproduct of the way our brains process information in a changing world. Or maybe we're missing something fundamental, a hidden law of physics, a deeper principle that explains why time seems irreversible, even when every equation suggests otherwise. The paradox remains unsolved. Time moves forward, but the universe itself refuses to explain why. The Non-Locality Paradox. There is a fundamental rule in physics. Nothing can travel faster than light. This speed limit is woven into the very fabric of space-time, ensuring that cause always precedes effect. Break this rule, and paradoxes emerge. Signals arriving before they were sent, information violating causality, and events rewriting their own past. Yet, deep in the world of quantum mechanics, something strange happens. Two particles, once entangled, remain mysteriously linked no matter how far apart they are. A measurement on one instantly influences the other, as if they communicate outside the normal flow of space and time. This is quantum entanglement, one of the most puzzling phenomena in physics. At first glance, it appears to break the fundamental rule. It suggests that information can travel instantaneously across any distance. But despite its eerie nature, it remains frustratingly useless for communication. No message, no data, no meaningful signal can be sent through entanglement alone. This contradiction is the non-locality paradox. If quantum mechanics allows for instant effects across space, why can't we use them to transmit information faster than light? To explore the problem, imagine Alice and Bob, two scientists with an entangled pair of particles. If Alice measures her particle, it immediately determines the state of Bob's, no matter how far away he is. But here's the issue. Alice has no control over what outcome she gets. The results are random, and Bob, upon checking his particle, sees only randomness too. There is no pattern, no deliberate encoding of information, just the strange, invisible link that always works but never communicates. This limitation isn't just a fluke. It's built into the mathematics of quantum mechanics itself. The moment Alice measures her particle, its state collapses into a definite value, and Bob's particle does the same. But because Alice's measurement is based on probability, she can't force a specific outcome. This means Bob's results remain unpredictable, no matter how instantaneously his particle reacts. It's as if the universe enforces a strict rule. You can observe entanglement, but you can't exploit it. Physicists have tried to explain this paradox in various ways. Some argue that entanglement hints at hidden variables, unknown aspects of reality that we simply haven't discovered yet. Others propose that information is fundamentally bound by deeper rules we don't yet understand. There are even those who believe entanglement is a sign that space itself is an illusion, a construct emerging from an underlying reality where distance and separation don't truly exist. Another possibility is that entanglement operates within a framework that prevents violations of causality. If we could send information instantly, we could theoretically send messages into the past, breaking the concept of cause and effect. Some physicists suspect that the paradox exists precisely because nature prevents such violations from occurring in the first place. But if entanglement can't send messages, what purpose does it serve? Some theories suggest that entanglement isn't about information transfer at all, but about maintaining the consistency of the universe at a deeper level. It may be a fundamental aspect of reality, one that ensures everything in the cosmos remains interconnected in ways we have yet to grasp. The non-locality paradox forces us to confront the limits of our understanding. It reveals a universe where connections exist beyond space and time, yet stubbornly refuse to be used. The rules of nature hold firm, but the reasoning behind them remains one of physics' greatest unresolved mysteries. Perhaps, in the future, a deeper theory will emerge, one that finally explains why the universe teases us with the impossible, but never lets us reach for it. The neutron star density paradox. A neutron star is one of the most extreme objects in the universe. Born from the violent death of a massive star, it is an object so dense that a single teaspoon of its material would weigh billions of tons. The gravitational pull on its surface is immense, strong enough to crush atoms, strip electrons away, and squeeze protons and electrons together to form an ocean of pure neutrons. Yet, despite this unimaginable density, a neutron star does not collapse into a black hole. This raises an unsettling question. Why not? Given that neutron stars pack more mass than the Sun into a sphere barely 20 kilometers across, they seem dangerously close to the tipping point. The density is so extreme that the force of gravity should, in theory, pull the entire structure into a singularity. And yet, they remain as neutron stars, teetering on the edge of collapse, but never quite crossing over. The answer lies in an obscure but powerful force: neutron degeneracy pressure. Just as electrons in an atom obey quantum mechanical rules that prevent them from being squeezed into the same state, neutrons obey similar principles. This quantum law, known as the Pauli exclusion principle, states that no two identical fermions, like neutrons, can occupy the same quantum state. When gravity tries to squeeze the neutrons into an even smaller space, this quantum pressure pushes back, keeping the star stable. But this explanation only goes so far. Neutron degeneracy pressure is an effective counterforce, but it is not limitless. If enough mass is added to a neutron star, beyond a certain threshold, known as the Tolman-Oppenheimer-Volkoff limit, the degeneracy pressure can no longer hold back gravity, and the star collapses into a black hole. The problem is, we don't know the exact limit. The boundary between the most massive neutron stars and the smallest black holes is still uncertain, and observations have found neutron stars that seem to exist in a mass range where they should, in theory, collapse, but don't. Even more perplexing is the fact that neutron stars may contain states of matter that we don't fully understand. At extreme densities, neutrons may break down into their fundamental components, quarks, forming what is sometimes called quark matter or a quark star. If such a state exists, it could mean that something even more exotic than neutron degeneracy pressure is preventing collapse, a force we have yet to understand. Another possible answer lies in the behavior of gravity itself. Our understanding of gravity, as described by general relativity, breaks down under extreme conditions. If neutron stars don't collapse when we expect them to, it could be a sign that our models of gravity need revision, especially at these extreme scales. Some physicists speculate that new physics, perhaps even modifications to relativity, might be at play, preventing neutron stars from collapsing in ways we haven't yet realized. The neutron star density paradox highlights a fundamental gap in our understanding of physics. We can describe how neutron stars form and behave, but we don't fully grasp why they stop just short of becoming black holes. Whether it's due to exotic states of matter, hidden quantum effects, or a deeper flaw in our understanding of gravity, the answer remains one of astrophysics' greatest mysteries. The pre-Big Bang paradox. The universe, as we know it, began with the Big Bang. Space, time, and matter all emerged from an infinitely dense and hot singularity nearly 13.8 billion years ago. Everything, galaxies, stars, planets, even the fabric of space itself, expanded outward from this point, forming the cosmos we now inhabit. But this leads to an unsettling question. What came before the Big Bang? At first glance, the question seems logical. In our everyday experience, every event has a cause. Every moment is preceded by another. If the universe had a beginning, shouldn't there have been something before it? However, according to our current understanding of physics, time itself began with the Big Bang. Asking what happened before the Big Bang is like asking what's north of the North Pole. It may not even be a meaningful question. General relativity describes how space and time are intertwined, and at extreme densities, such as those of the early universe, our familiar notions of time break down. The equations suggest that as we rewind cosmic history, time becomes increasingly distorted until it effectively ceases to exist at the singularity. If time itself was created in the Big Bang, then there was no before in the conventional sense, because before requires the existence of time. However, this answer is deeply unsatisfying. If the universe truly emerged from nothing, what caused it? Did reality simply pop into existence without reason? Or is our understanding of time incomplete? One possibility is that the Big Bang wasn't the absolute beginning, but a transition, a moment in a much larger, eternal cosmic cycle. Some theories suggest a big bounce, where the universe expands and contracts endlessly, with each collapse giving rise to a new expansion. In this view, our universe is just one phase in an infinite sequence of cosmic rebirths. Others propose a multiverse scenario, where our Big Bang was simply one event in a much grander cosmic structure. Perhaps quantum fluctuations in a larger timeless reality led to the birth of our universe. In such a model, before the Big Bang could refer to an entirely different kind of existence, one governed by unknown physics that doesn't require time as we know it. String theory introduces another possibility, the ekpyrotic model, where our universe was created by the collision of higher dimensional brains in a hidden dimension. If true, then time may stretch beyond our Big Bang, existing in a way we don't yet understand. And then, there is the most unsettling idea of all. Causality itself may not apply beyond the Big Bang. Perhaps time, cause, and effect are merely emergent properties of our universe, and beyond them, the concept of before is meaningless. The pre-Big Bang paradox forces us to confront the limits of human understanding. If time began at the Big Bang, what does it mean to ask what came before? Is the question itself flawed? Or are we simply not yet equipped to grasp the true nature of reality? The speed of Causality Paradox. The speed of light, 299,792,458 meters per second, is often thought of as the ultimate speed limit of the universe. Nothing, not even information, can travel faster than this cosmic speed limit. Yet, when we observe the vast expanse of the cosmos, We see regions of space that should have never been able to interact with each other, yet they look nearly identical. How is this possible? The paradox arises when we consider the horizon problem, the mystery of how distant parts of the universe appear to have been in thermal equilibrium, despite never having had the chance to exchange information. The cosmic microwave background radiation, CMB, the afterglow of the Big Bang, is nearly uniform across the entire observable universe. This would make sense if all these regions had once been in close contact, allowing them to balance their temperatures. But given the known expansion rate of the universe, these regions should have never been able to communicate with each other. There simply hasn't been enough time for light, or any signal, to travel between them. If information is restricted by the speed of light, then how did causality manage to synchronize these vastly separated regions? How did they all end up at nearly the same temperature and structure when they should have evolved independently? One proposed solution to this paradox is cosmic inflation. According to this theory, in the very first fraction of a second after the Big Bang, the universe underwent an unimaginably rapid expansion, far exceeding the speed of light, though not violating relativity, since space itself was expanding. Before this expansion, the universe was much smaller, meaning that all regions could have interacted and reached equilibrium. Then, as inflation stretched space apart, these causally connected regions became the vast, seemingly disconnected parts of the universe we see today. However, inflation is still a hypothesis, not a confirmed law of nature. Some physicists question whether it truly solves the problem, or just shifts it to another unexplained mechanism. If inflation didn't occur, we would need an alternative explanation. Perhaps some unknown physics governing the early universe that allowed for a deeper form of connectivity beyond the speed of light. Another approach comes from quantum entanglement, which suggests that particles can be instantaneously correlated across vast distances. While entanglement itself doesn't allow for faster-than-light communication, some theorists speculate that deeper quantum mechanisms could play a role in how causality operates on a cosmic scale. Then there's the more radical possibility. Our assumptions about causality itself may be incomplete. If the fabric of space-time allows for hidden variables, extra dimensions, or retrocausality, effects influencing causes in the past, then the limits we currently place on the speed of information transfer may not be fundamental after all. The speed of causality. Paradox forces us to question the very nature of connectivity in the universe. If nothing can travel faster than light, how did distant parts of the cosmos manage to synchronize? Did inflation provide the answer? Or is there something even deeper about space-time and causality that we have yet to understand? The vacuum energy paradox. At the heart of quantum field theory lies a strange concept: vacuum energy. The idea that even in a perfect vacuum, where no matter or radiation exists, space is still filled with fluctuating energy. The vacuum is far from empty. It's teeming with virtual particles constantly appearing and disappearing, an invisible dance of creation and annihilation. In quantum mechanics, even the emptiest of spaces is alive with these fluctuations, meaning that the vacuum itself has an associated energy. This vacuum energy is thought to be enormous. In fact, theoretical predictions based on quantum field theory suggest that the vacuum energy is so large that it should have catastrophic consequences for the universe. If the energy stored in the vacuum were to manifest, it would create immense gravitational effects so powerful that the universe should have collapsed in on itself long ago. The paradox comes into play when we look at the observable universe. If the vacuum energy is as enormous as we predict, why hasn't it caused the universe to collapse immediately? Why are we not observing a universe that has long since imploded due to this incredible energy? The answer isn't clear, and it challenges the very foundations of our understanding of space, time, and energy. In principle, vacuum energy should have a significant impact on the expansion of the universe. One might expect it to act as a repulsive force, pushing everything apart due to the overwhelming amount of energy present in the void. In fact, this is one of the reasons that scientists suspect vacuum energy may play a role in the accelerated expansion of the universe, a phenomenon observed through the mysterious force known as dark energy. Dark energy is thought to account for about 70% of the energy content of the universe and appears to be driving its rapid expansion. But the relationship between vacuum energy and dark energy is still a subject of intense debate. The sheer scale of vacuum energy is another problem. Quantum field theory predicts that the vacuum energy density should be on the order of 10 to the 120th power times greater than the amount that is actually observed. This discrepancy is not just a small difference, it's an unfathomable gap. It's like trying to balance a pencil on its tip in a hurricane and expecting it to stay perfectly still for billions of years. The mismatch is so extreme that it's hard to believe our current understanding of vacuum energy is anywhere near accurate. So, what gives? Why doesn't the enormous vacuum energy wreak havoc on the universe? Physicists have proposed a few possible answers, but none are entirely satisfactory. One potential explanation involves fine-tuning. This idea suggests that the vacuum energy's effects are somehow being cancelled out or suppressed by some unknown mechanism. In this view, there's an as-yet undiscovered force, particle, or principle that compensates for the vast energy in the vacuum, leaving us with only a small, almost negligible effect on the universe. This fine-tuning, however, seems highly improbable. The precision required to perfectly cancel out such enormous energy over vast cosmological scales seems almost too improbable to be true. The universe would have to be set up just right, with everything aligning perfectly, which raises uncomfortable questions about the nature of our cosmos and why it exists the way it does. Another possible solution involves the nature of gravity itself. General relativity, Einstein's theory of gravity, is our best description of how massive objects interact with space-time, but it doesn't include quantum effects. In quantum mechanics, particles can influence each other through forces that are not described by general relativity. Some theorists propose that vacuum energy doesn't interact with gravity in the way we think, which could prevent its gravitational effects from causing a collapse. If gravity works differently on a quantum scale, or interacts with vacuum energy in a unique way, it could explain why we don't observe the expected collapse. Moreover, some have speculated that the vacuum energy problem may not be a problem at all, at least not in the way we understand it. It's possible that our current framework for understanding energy and space is too limited. Perhaps the equations we use to calculate vacuum energy are based on assumptions that don't hold at the scales of the universe. For instance, if the vacuum energy interacts with other dimensions or has a connection to forces outside our understanding, then the calculations we rely on could be fundamentally flawed. There's also the possibility that our definitions of vacuum and space itself are incomplete. If space is not truly empty, but instead is a fabric that has properties we do not yet understand, then perhaps the vacuum energy we've measured is not even the full picture. Extra dimensions, as suggested by string theory, could be influencing the way we perceive vacuum energy. In such a scenario, the energy stored in the vacuum may not actually be as immense as it seems, or it could manifest in ways we haven't yet discovered. Lastly, there's the more radical possibility that our perception of vacuum energy is incomplete, and that we are measuring something entirely different. Could the fluctuations we observe be the result of interactions between hidden variables, or perhaps energy stored in alternate states of reality that only manifest under specific conditions? Until we fully understand the quantum nature of the universe, it's impossible to rule out more exotic explanations. The vacuum energy paradox presents us with one of the most frustrating and fundamental challenges in modern physics. The predictions suggest a universe that should have collapsed under its own weight long ago, yet we continue to observe a stable cosmos. Is there some unknown force at work? A flaw in our understanding of gravity, energy, or space itself? Or perhaps we are missing an entirely new principle that will change how we view the universe? Until we uncover the answers, the vacuum energy paradox will remain a mysterious, unresolved riddle at the heart of quantum cosmology. The twin paradox, also known as the time dilation paradox, is a well-known thought experiment that arises from Einstein's theory of special relativity. This paradox challenges our intuitive understanding of time and highlights the counterintuitive nature of the universe when objects move at high speeds. The basic scenario involves two identical twins. One remains on Earth, while the other embarks on a journey into space, traveling at speeds close to the speed of light before returning. When the traveling twin comes back, he or she will have aged significantly less than the twin who stayed on Earth. This creates the paradox, as it raises the question: how is it possible for two individuals who started as identical to experience different amounts of time passing? The root of the paradox lies in the concept of time dilation, a phenomenon predicted by Einstein's theory of relativity. Time dilation suggests that time moves at different rates for observers in different reference frames, especially when one of those observers is moving at relativistic speeds, close to the speed of light. In this case, the traveling twin is moving at near light speed, which causes time to pass more slowly for them relative to the twin who remains stationary on Earth. This slowing down of time for the traveling twin leads to them aging less, even though both twins experience time normally from their own perspectives. At first glance, the paradox seems like a contradiction. After all, from the perspective of the traveling twin, they are stationary in their own reference frame, and it is the earthbound twin who is moving away at near light speed. By the principle of relativity, both observers should experience time dilation in the same way. However, the situation becomes complicated when we factor in that the traveling twin does not remain in a single inertial frame throughout the journey. The key to resolving the paradox is to recognize that the twin traveling through space experiences acceleration and deceleration during the trip, which breaks the symmetry of the situation. To illustrate this further, we need to analyze the journey more carefully. The traveling twins trip involves several stages: accelerating to high speed, cruising at near light speed for a period of time, decelerating, and then turning around and returning to Earth. The acceleration phases are crucial because, unlike the earthbound twin, the traveling twin does not remain in an inertial frame of reference throughout the entire journey. The twin on Earth remains at rest in one reference frame, experiencing no acceleration, while the traveling twin constantly changes their velocity during the trip. In Einstein's theory, time dilation occurs when an object is moving at a constant velocity relative to another object, and the faster an object moves, the slower time passes for it, relative to a stationary observer. However, the traveling twin undergoes acceleration and deceleration as part of their journey, and it is this non-inertial motion that causes the asymmetry between the two twins' experiences. The earthbound twin remains in an inertial frame for the entire duration of the experiment, while the traveling twin switches frames multiple times, once when accelerating away from Earth, again when decelerating, and yet again when accelerating back toward Earth. These changes in velocity are what break the symmetry of the situation and explain why the traveling twin ages more slowly. The resolution to the paradox is grounded in the fact that the two twins are not in identical situations. The earthbound twin remains in a single, unchanging reference frame, while the traveling twin is constantly changing frames of reference due to their acceleration. The fact that the traveling twin is not always in an inertial reference frame leads to a different experience of time for them compared to the twin on Earth. The mathematical explanation for time dilation involves the Lorentz factor, which is derived from the equations of special relativity. The Lorentz factor describes how time slows down as an object's speed increases. At speeds approaching the speed of light, the factor becomes very large, meaning that time for the traveling twin slows dramatically compared to the twin who stays on Earth. This is why, after the journey, the traveling twin is younger than the earthbound twin. In practice, time dilation has been confirmed through experiments involving fast-moving particles and highly accurate clocks. For instance, atomic clocks placed on satellites moving at high velocities experience time at a slightly slower rate than those on Earth, as predicted by special relativity. This effect is real and measurable, although it is minuscule in everyday life. However, if we were ever to achieve near-light-speed space travel, the effects of time dilation would become much more pronounced, as demonstrated by the twin paradox. The paradox also raises fascinating questions about the nature of time itself. In everyday life, we tend to think of time as a constant, universal force that passes at the same rate for everyone. But the twin paradox demonstrates that time is not a universal constant. It is relative to the observer's state of motion. The faster you move through space, the slower you move through time. This insight challenges our traditional understanding of time and forces us to rethink our assumptions about how time works. While the twin paradox may seem like a purely theoretical exercise, it has important implications for real-world physics, particularly in the realm of space travel. If humanity ever develops the technology to travel at relativistic speeds, time dilation will become a crucial factor in planning long-duration space missions. Astronauts traveling at high speeds may experience time at a much slower rate than those on Earth, meaning that years or even decades could pass for those on Earth, while only a few years pass for the astronauts. This is a concept that has been explored in science fiction, but it is grounded in real physics. Furthermore, the paradox has profound philosophical implications. If time is relative, then our experience of the passage of time is not universal. It depends on our state of motion. This leads to deep questions about the nature of reality, the passage of time, and the relationship between space and time. The twin paradox forces us to reconsider our fundamental understanding of the universe and our place in it. In conclusion, the twin paradox, or time dilation paradox, is not just a fascinating thought experiment. It is a demonstration of one of the most profound and mind-bending aspects of Einstein's theory of special relativity. It shows us that time is not an absolute, unchanging force, but rather something that is relative to the observer's motion. The paradox also reminds us of the complexity and wonder of the universe, challenging our perceptions of time, aging, and the possibilities of space travel. The black hole. Information paradox is one of the most perplexing and debated issues in modern theoretical physics. It stems from the apparent conflict between two fundamental principles: the law of conservation of information in quantum mechanics, and the behavior of information when it falls into a black hole, as predicted by general relativity. The paradox arises from the observation that, according to general relativity, anything that falls into a black hole, whether it's matter, light, or even information, appears to be lost beyond the event horizon, the boundary beyond which nothing can escape. However, quantum mechanics insists that information cannot be destroyed. This conflict between the two theories forms the crux of the black hole information paradox. To understand the paradox, it's essential to first grasp the concepts of quantum mechanics and general relativity. Quantum mechanics is the branch of physics that deals with the behavior of particles at the smallest scales, and one of its key tenets is that information about a system, whether it's the position or state of a particle, cannot be completely erased. The conservation of information is a cornerstone of quantum theory, meaning that information about the physical state of a system should always be preserved, even if the system evolves over time. In contrast, general relativity, which describes the behavior of large-scale objects like stars and black holes, predicts that once information crosses the event horizon of a black hole, it is forever lost to the outside universe. Black holes themselves are regions in space where gravity is so strong that not even light can escape. The event horizon marks the point of no return. Once something crosses it, it cannot escape. According to classical general relativity, everything that falls into a black hole, including matter and energy, is crushed to a singularity, a point of infinite density at the center of the black hole. However, this description does not account for quantum mechanical effects, leading to the paradox. The problem arises when considering what happens to the information about the objects that fall into a black hole. If all information about an object is lost when it crosses the event horizon, then quantum mechanics would be violated. This is because quantum mechanics dictates that no information can be lost in a closed system. But if information is destroyed, as general relativity suggests when matter falls into a black hole, this would create a fundamental conflict between the two theories. One of the most significant aspects of this paradox involves Hawking radiation, a phenomenon proposed by physicist Stephen Hawking in 1974. Hawking radiation is a theoretical prediction that black holes should slowly radiate energy due to quantum effects near the event horizon. This radiation causes black holes to lose mass over time, eventually leading to their evaporation. The issue, however, is that when a black hole evaporates, it seems to take all the information that fell into it with it. The black hole's final explosion, as it evaporates completely, appears to be information-free, meaning that the information about the particles that fell into the black hole would be lost forever. This leads to the so-called information loss paradox. If the information that fell into a black hole is lost when the black hole evaporates, it would contradict quantum theory's insistence that information must be conserved. This paradox has become one of the central mysteries in theoretical physics, forcing scientists to reconsider the foundations of quantum mechanics and our understanding of gravity. Over the years, several theories have been proposed to resolve the black hole information paradox. One possibility is that the information is not actually lost, but is instead encoded in the Hawking radiation emitted by the black hole. Some researchers suggest that this information is somehow encoded in the quantum states of the radiation particles, which could carry the lost information back to the universe. This idea is known as the information retrieval hypothesis. According to this view, while the information may be scrambled and hidden within the radiation, it is not truly lost. The process of decoding this information could eventually reveal the details of the particles that fell into the black hole, even after the black hole has evaporated. Another possibility is that the information may be stored at the event horizon itself, potentially in the form of quantum entanglement. This idea was proposed by physicists such as Juan Maldacena and others, who suggested that the event horizon may act as a kind of holographic surface, where all the information about the particles that have fallen into the black hole is encoded. This theory is linked to the holographic principle, which is a conjecture in theoretical physics, suggesting that all the information within a region of space can be represented as a lower dimensional surface. In this view, the event horizon of a black hole would encode all the information of the objects that have fallen into it. And this information would not be lost, but could eventually be retrieved through quantum processes. A third proposal suggests that the black hole's singularity may not exist in the way we currently understand it. Some theories in quantum gravity, such as loop quantum gravity, suggest that singularities might not be as singular as general relativity predicts. Instead of a point of infinite density, there might be a way to preserve information at the core of a black hole. If this is the case, then the information about matter that falls into a black hole could be preserved in some form, even if it is not immediately accessible. Despite these intriguing ideas, there is no consensus among physicists about how to resolve the paradox, and it remains one of the biggest unsolved problems in modern physics. The black hole information paradox touches on fundamental questions about the nature of reality, the flow of time, and the ultimate limits of our understanding of the universe. It is closely related to the quest for a theory of quantum gravity, which seeks to reconcile the seemingly incompatible frameworks of general relativity and quantum mechanics. The resolution of the black hole information paradox could have profound implications for our understanding of the universe. It may shed light on the nature of black holes, the fabric of space-time, and the very structure of the cosmos. It might also offer insights into the nature of quantum mechanics and how information is stored and processed at the most fundamental level. In conclusion, the black hole information paradox represents a deep and unresolved challenge in theoretical physics. It presents a conflict between two of the most successful and foundational theories of modern science: general relativity and quantum mechanics. The resolution of this paradox may require a breakthrough in our understanding of both quantum gravity and the nature of black holes, and could ultimately provide new insights into the fundamental workings of the universe. Until that time, the paradox continues to fascinate and inspire physicists and cosmologists as they strive to uncover the true nature of black holes and the information they contain. The Olbers Paradox is a thought experiment that has puzzled astronomers and philosophers for centuries. It is named after the German astronomer Heinrich Wilhelm Olbers, who first formalized the question in 1823, though the paradox itself was discussed earlier by other thinkers. The paradox asks, if the universe is infinite and filled with an infinite number of stars, why isn't the night sky completely bright? After all, every line of sight in the night sky should eventually hit a star, meaning that the entire sky should glow as brightly as the surface of the sun. Instead, when we look up at night, we see a vast expanse of darkness punctuated by distant stars. This question seems to contradict our expectations, especially given the assumptions of an eternal static universe. The basic premise of Olbers' paradox is built on the idea of an infinite static universe. In such a universe, stars are evenly distributed throughout space, and light from these stars should travel indefinitely, never fading away. If this were the case, the night sky would be bright, because no matter where you look, your line of sight would eventually intersect a star. The paradox becomes particularly puzzling when we consider the infinite nature of space. With an infinite number of stars and an infinite number of opportunities for light to travel, it would seem that the universe should be bathed in an almost blinding light at all times. This problem had been a source of confusion for centuries. However, The resolution of the Olbers Paradox lies in the understanding of the universe's finite age, the expansion of space, and the limitations on how far light can travel. The first key piece of the solution to the paradox is the finite age of the universe. The universe is not eternal. It began with the Big Bang, around 13.8 billion years ago. This means that the universe has a definite age, and light from stars beyond a certain distance has not had enough time to reach us. In other words, the light from the farthest stars has not had enough time to travel the vast distances necessary to reach Earth. This is often referred to as the observable universe, the region of space from which light has had time to travel to Earth since the beginning of the universe. Anything outside of this region is beyond our observational reach, and the light from those distant stars has not yet arrived. Moreover, as light travels through space, the expansion of the universe stretches it. This is known as the redshift effect. The expansion of space causes the wavelengths of light to stretch, shifting the light towards the red end of the spectrum. For extremely distant stars, the light may be stretched so much that it falls outside of the visible spectrum entirely, becoming infrared or even radio waves. This means that even if there are stars far enough away to have emitted light that could eventually reach Earth, that light would no longer be visible to us. It would be redshifted out of the visible range, leaving the night sky dark. Another critical aspect of the resolution involves the distribution of stars and the geometry of space. While the universe may be infinite, the stars within it are not distributed uniformly in space. In fact, the stars are spread out in galaxies, which are themselves separated by vast expanses of empty space. Light from stars in distant galaxies is not guaranteed to reach Earth, because the intervening space may be vast enough that the light does not encounter a direct path to us. Additionally, some stars may be obstructed by cosmic dust and gas, further limiting the light that reaches our eyes. The Olbers Paradox also draws attention to the changing nature of the universe over time. As the universe continues to expand, the distance between galaxies increases, meaning that the amount of light that can reach us from distant stars decreases. In a static, eternal universe, the light from every star would eventually reach us. But the actual universe we live in is dynamic and evolving. The ongoing expansion of space prevents the night sky from becoming uniformly bright, and this fact alone helps to explain why the darkness of the night sky persists, despite the theoretical infinity of stars. The dark night sky, in fact, provides us with valuable clues about the nature of the universe. The fact that the universe is expanding and that the light from distant stars is redshifted supports the current model of the Big Bang and the expanding universe. This model is a direct consequence of the observation that galaxies are moving away from us, and their light is increasingly shifted towards the red end of the spectrum, the farther away they are. This discovery, which was first made in the 1920s by Edwin Hubble, has since been confirmed through numerous observations and remains one of the cornerstones of modern cosmology. Further insight into the resolution of the Olbers Paradox came with the development of the concept of dark energy. Dark energy is a mysterious form of energy that is driving the accelerated expansion of the universe. This phenomenon not only explains the redshift of light from distant galaxies, but also contributes to the fading of light from far-off stars. As the universe expands more rapidly, light from the most distant objects becomes even less likely to reach us. In conclusion, the Olbers Paradox highlights an apparent contradiction between our expectations of an infinite universe and the reality of a dark night sky. The resolution of the paradox lies in several key concepts. The finite age of the universe, the expansion of space, and the limitations on how far light can travel. The finite time since the Big Bang combined with the stretching of light due to the expanding universe, ensures that the night sky remains dark, despite the infinite number of stars. By understanding the nature of the universe's expansion, the redshift effect, and the observable universe, we can begin to reconcile the paradox and appreciate the true nature of the cosmos. The darkness of the night sky is not a mystery, but a result of the dynamic and ever-changing universe in which we live. The heat-death paradox. According to the second law of thermodynamics, the universe is constantly moving toward a state of maximum entropy, or heat death, where all energy becomes evenly distributed and no useful work can be done. In this state, all differences in temperature disappear, stars burn out, and galaxies drift apart until nothing remains but a cold, dark expanse of low-energy particles. If this process has been occurring for an infinite amount of time, a troubling question arises. Why hasn't the universe already reached heat death? This paradox challenges our fundamental understanding of entropy and the nature of time. The second law states that in a closed system, entropy, often described as disorder or randomness, always increases. Over long enough timescales, this means all available energy will spread out, making complex structures like galaxies, stars, and even life unsustainable. Given that entropy always increases, and that time appears to stretch indefinitely into the past, the paradox suggests that the universe should already be in a state of heat death. Yet we observe a cosmos full of activity, with galaxies forming, stars shining, and planets orbiting. One possible resolution to this paradox is that the universe did not always exist in its current form. If the universe had a definite beginning, such as the Big Bang, then entropy would have started at an extremely low level, allowing time for its gradual increase. The universe as we know it is only around 13.8 billion years old, an immense time span, yet far from infinite. This suggests that there simply hasn't been enough time for heat death to take effect. Another possible explanation involves the expansion of the universe. Observations show that space itself is stretching due to dark energy, an unknown force driving cosmic acceleration. As the universe expands, it affects the distribution of energy, possibly delaying or even altering the ultimate fate of entropy. Some physicists propose that this expansion creates new space faster than entropy can increase, preventing the universe from ever reaching thermal equilibrium. Additionally, there is the possibility that the universe is not a truly closed system. The second law of thermodynamics applies to isolated systems, where no energy or matter enters or exits. If the universe is part of a larger multiverse, then energy could be entering or leaving our observable cosmos in ways we do not yet understand. This could mean that entropy behaves differently on a grander scale, challenging the assumption that heat death is inevitable. Another speculative resolution involves cyclical cosmology, the idea that the universe undergoes endless cycles of expansion, contraction, and rebirth. Some theories suggest that after reaching a certain point of expansion, the universe could collapse in a big crunch, resetting entropy to a low state and initiating another Big Bang. If this cycle repeats indefinitely, then entropy never has an infinite amount of time to increase, sidestepping the paradox entirely. On a smaller scale, modern physics continues to explore how entropy interacts with quantum mechanics. Some theories suggest that information and entropy are conserved in ways we do not yet fully understand. Black holes, for instance, are thought to trap entropy inside their event horizons. Yet Stephen Hawking's theories propose that they eventually evaporate through radiation. If this radiation somehow retains the information once lost, inside a black hole. It could suggest that entropy behaves differently at quantum levels than previously assumed. The heat-death paradox ultimately forces us to confront some of the deepest mysteries in physics: the nature of time, the structure of the cosmos, and the ultimate fate of everything that exists. If entropy truly dictates the end of the universe, then a dark, lifeless future may be inevitable. However, if new physics emerges that challenges our understanding of thermodynamics, then the final destiny of the cosmos may be far more complex than we currently imagine. The Big Rip Paradox. The universe is expanding, a fact first observed by Edwin Hubble in the 1920s. However, the nature of this expansion has puzzled scientists for decades. Instead of slowing down due to gravitational attraction, as once expected, observations show that the universe's expansion is accelerating. This acceleration is driven by an unknown force called dark energy, which makes up roughly 68% of the total energy in the cosmos. If dark energy continues to push the fabric of space apart at an increasing rate, it could eventually lead to a catastrophic scenario known as the Big Rip. In this hypothetical future, the expansion of the universe does not simply continue indefinitely. It accelerates to the point that it tears everything apart. Galaxies that are currently held together by gravity would begin to separate. Over time, the forces binding individual solar systems, planets, and even atoms themselves would be overcome by the relentless stretching of space. Eventually, even the fundamental particles that make up matter could be torn apart, leaving behind nothing but isolated fragments adrift in an ever-expanding void. The paradox arises when we consider the ultimate fate of time and space themselves. If the universe is ripped apart entirely, then what happens after everything ceases to exist? What does after even mean, in a reality where time itself may break down? The paradox forces us to question whether time is an absolute concept, or if it is merely a property of the universe that ceases to function when space is destroyed. One possible resolution to this paradox is that time may not continue in the way we understand it. If time is intrinsically linked to the structure of space, then the destruction of space could mean the end of time itself. This would imply that there is no after the Big Rip. Existence simply ceases in every conceivable way. However, this idea is difficult to reconcile with our understanding of physics, as it suggests a true void beyond even quantum fluctuations and virtual particles. Another possibility is that the destruction of space is not the end, but rather a transition. Some physicists speculate that extreme cosmic events, such as the Big Rip, could lead to the birth of new universes. If space is torn apart at a fundamental level, it could trigger conditions similar to those of the Big Bang, leading to a rebirth of time and space in a completely new form. This would align with some models of quantum gravity, where space-time itself is not a continuous fabric, but a dynamic structure that can break and reform under extreme conditions. The Big Rip Paradox also raises questions about the nature of dark energy. Scientists currently do not fully understand what dark energy is, only that it behaves like an unseen force, pushing the universe apart. If dark energy remains constant, the universe may continue to expand forever without ripping apart. However, if dark energy grows stronger over time, then the Big Rip scenario becomes more likely. Understanding the true nature of dark energy is one of the greatest challenges in modern physics, as it holds the key to predicting the fate of the universe. One interesting consequence of the Big Rip scenario is its implications for black holes. Black holes are currently considered some of the most stable objects in the universe, capable of lasting for trillions of years before slowly evaporating due to Hawking radiation. However, in a universe destined for the Big Rip, even black holes would eventually be torn apart, releasing all the information they once contained. This could provide insights into the relationship between black holes, entropy, and the ultimate fate of information in the cosmos. Ultimately, the Big Rip paradox challenges our understanding of time, space, and the very structure of reality. If the laws of physics break down under extreme expansion, then our current models may be incomplete. Whether the universe is destined to expand forever, collapse in a big crunch, or be torn apart in a big rip, remains one of the most profound mysteries in cosmology. Until we gain a deeper understanding of dark energy and the fundamental nature of space-time, the true fate of the universe, and what, if anything, lies beyond it, will remain an open question. The White Hole Paradox. Black holes are among the most mysterious and powerful objects in the universe, possessing gravitational forces so strong that not even light can escape their grasp. However, according to Einstein's equations in general relativity, if black holes exist, then their theoretical counterparts, white holes, should also exist. A white hole would function as the exact opposite of a black hole. Rather than pulling everything in, it would constantly expel matter and energy while preventing anything from entering. Yet, despite extensive searches, no white holes have ever been observed, leading to one of the great mysteries in theoretical physics, the White Hole Paradox. The concept of a white hole arises naturally from solutions to Einstein's field equations. When solving for an object with immense gravitational pull, physicists derive the Schwarzschild metric, which describes both black holes and white holes. While a black hole has an event horizon from which nothing can escape, a white hole theoretically has an event horizon that nothing can enter. This would mean that anything inside a white hole is permanently trapped and can only move outward, continuously ejecting energy and matter into the universe. Despite its mathematical foundation, the fact that we have never detected a white hole raises a significant paradox. If black holes exist in reality, why haven't we observed their predicted opposites? One possible explanation is that white holes are inherently unstable. Unlike black holes, which naturally form from the collapse of massive stars, there is no known physical process that could create a white hole in nature. Furthermore, the moment a single particle, or even a small fluctuation in energy, attempted to interact with a white hole, it would theoretically collapse instantly, making its existence fleeting at best. This instability might explain why we do not see white holes in the observable universe. Another fascinating hypothesis is that white holes might exist, but are concealed from us in ways we don't yet understand. Some theoretical models suggest that black holes and white holes could be connected through wormholes, shortcuts in space-time that link distant parts of the universe. If this were the case, material falling into a black hole might not be lost forever, but could re-emerge elsewhere through a white hole. However, modern physics suggests that such wormholes would likely be extremely unstable, collapsing almost immediately due to quantum fluctuations. One of the most radical and intriguing ideas related to white holes is the possibility that the Big Bang itself might have been a massive white hole event. If white holes exist, it's conceivable that our universe began as the ultimate white hole explosion, ejecting all the matter and energy we see today. This idea provides an alternative perspective on the origins of the cosmos, though it remains speculative due to the lack of direct evidence. If this theory were true, it could imply that our universe is part of a larger cyclic system, where black holes in one universe give birth to white holes in another. Astrophysicists have also speculated that certain high-energy cosmic phenomena might be linked to white holes. Some have suggested that gamma-ray bursts, immensely powerful explosions that release vast amounts of energy, could be observational evidence of white holes ejecting matter into the universe. However, current models of gamma-ray bursts do not require white holes to explain them, and there is no direct observational data linking the two. The white hole paradox highlights a fundamental challenge in modern physics. Our best mathematical models predict that white holes should exist, yet we see no evidence of them. This discrepancy forces us to question whether our current theories are incomplete or whether white holes exist in a way that is beyond our observational capabilities. Could they exist in another universe? Might they be hiding within the structure of space-time itself? Or is there a deeper flaw in our understanding of gravity and relativity? Until these questions are answered, white holes remain one of the most fascinating and elusive concepts in theoretical physics. Whether they turn out to be a real part of the universe or merely a mathematical curiosity, the search for white holes pushes the boundaries of our understanding of space, time, and the fundamental nature of reality itself. The Youngness Paradox. The universe is approximately 13.8 billion years old, and in that vast expanse of time, countless stars and planets have formed, creating the potential for life to emerge elsewhere. Given the immense age of the cosmos, some alien civilizations should be billions of years older than humanity. If intelligent life is common, it stands to reason that at least some advanced extraterrestrial species would have had ample time to explore, colonize, or at the very least, leave detectable traces of their existence. Yet, as far as we can tell, the universe appears silent and empty. This contradiction is known as the Youngness Paradox, a troubling variant of Fermi's Paradox, which forces us to ask, why do we seem to be among the first, if not the only, intelligent civilizations? One of the key assumptions behind the Youngness Paradox is that technological progress compounds over time. A civilization that is even 1,000,000 years ahead of us should theoretically possess capabilities beyond our imagination, perhaps achieving interstellar travel, artificial superintelligence, or galaxy-scale engineering projects. If civilizations like this had arisen long before humanity, their influence should be unmistakable, whether through megastructures like Dyson spheres, signals traveling across interstellar distances, or even deliberate contact efforts. Yet, we observe no such evidence. Several hypotheses attempt to resolve this paradox. One possibility is that intelligent life is far rarer than we assume. The emergence of complex, intelligent beings may require an extraordinarily unlikely sequence of events, so improbable that Earth is one of the only planets where it has ever occurred. This idea aligns with the rare Earth hypothesis, which argues that while microbial life might be common, the leap to intelligence is an exceedingly rare phenomenon. Another explanation is that civilizations might self-destruct before they can reach a stage of interstellar expansion. This idea, known as the Great Filter, suggests that at some point in technological advancement, nearly all civilizations encounter a catastrophic barrier, such as nuclear war, environmental collapse, runaway artificial intelligence, or other existential threats, that prevents them from progressing any further. If this filter exists ahead of us, it may mean that human civilization is also doomed to collapse before achieving widespread space colonization. Alternatively, it is possible that advanced extraterrestrial civilizations exist, but deliberately avoid contact with younger civilizations like ours. This concept, sometimes called the zoo hypothesis, proposes that highly advanced species choose to observe us from afar without interfering, perhaps to allow us to develop naturally, or because they see us as too primitive to interact with. Similarly, another theory suggests that intelligent civilizations may communicate only under specific conditions, using methods we have yet to discover, leaving us unaware of their existence. There is also the possibility that we are simply looking in the wrong way. Our current methods of searching for extraterrestrial life, such as listening for radio signals, might be inadequate if advanced civilizations use communication technologies that are beyond our comprehension. If alien civilizations communicate via quantum entanglement, neutrino beams, or some other exotic mechanism, we might be completely oblivious to their existence. The Youngness Paradox challenges our assumptions about life in the universe and raises profound questions about our place in the cosmic timeline. Are we truly one of the first intelligent species to arise? Is there an inevitable fate awaiting civilizations that prevents them from spreading? Or are we just one of many civilizations that exist but remain hidden from one another? Until we find definitive evidence of extraterrestrial intelligence, or lack thereof, the paradox remains one of the greatest mysteries of modern science. The Antigravity Paradox challenges our understanding of gravitational forces and the large-scale structure of the universe. Gravity, as we know, is a force that attracts all objects with mass toward one another. According to the theory of gravity, galaxies, stars, and even planets should eventually collapse under the immense force of their own gravity. If this were the case, galaxies would gradually be pulled inward over time, and the universe would exhibit a tendency to contract rather than expand. Yet, what we observe is quite the opposite. Galaxies are moving away from each other, and the universe as a whole is expanding. This phenomenon was first observed by astronomers like Edwin Hubble in the early 20th century, who discovered that distant galaxies are receding from us, with their speeds increasing the farther they are. This discovery, known as the Hubble law, suggested that the universe is not static, as once thought, but instead is expanding in all directions. The paradox arises from the fact that, if gravity attracts all matter, we would expect the expansion of the universe to slow down over time, or even reverse. Instead, the expansion continues to accelerate, leaving scientists puzzled about the forces at play. To explain this paradox, physicists have proposed the existence of an unknown force that is working against gravity on the largest cosmic scales. This force is now referred to as dark energy, an enigmatic and poorly understood form of energy that makes up about 68% of the universe's total energy content. Unlike gravity, which attracts objects toward one another, dark energy seems to push objects apart, accelerating the expansion of space itself. The discovery of dark energy came in the late 1990s when two independent teams of astronomers were studying type Ia supernovae, the explosive deaths of certain types of stars. They observed that these supernovae were farther away than expected, based on the assumption that the universe's expansion was slowing down. Instead, the supernovae appeared to be accelerating away from us. This led to the realization that something was driving the universe's expansion faster than gravity alone would permit. Dark energy, while a powerful explanatory tool, remains largely mysterious. We know it exists because of its effects on the universe's expansion, but we don't yet understand what it is or how it works on a fundamental level. The leading theory proposes that dark energy is a cosmological constant, a uniform energy density that fills space. This theory, however, does not explain why the constant appears to have the exact properties required to accelerate cosmic expansion. Other hypotheses suggest that dark energy could be related to the vacuum energy of empty space itself, or it could be a result of modifications to the theory of gravity at very large scales. The presence of dark energy has profound implications for the future of the universe. If dark energy continues to drive the accelerated expansion of the universe, it could lead to a big freeze, in which galaxies, stars, and other cosmic structures move so far apart that they eventually become isolated from one another, and the universe reaches a state of cold, empty void. In this scenario, galaxies and stars will no longer interact, and life, if it exists elsewhere, would likely cease to thrive. However, the true nature of dark energy remains elusive, and its discovery has only deepened the paradox of the universe's expansion. How could a force like gravity, which is so powerful on small scales, be so easily counteracted by a force that we don't fully understand? Why does dark energy appear to dominate on large scales, but leave local gravitational interactions relatively unaffected? These questions are central to the quest for a unified theory of everything, one that would seamlessly combine the principles of gravity, quantum mechanics, and the mysteries of dark energy. As our understanding of the universe grows, the Antigravity Paradox will likely remain at the forefront of cosmological research, challenging scientists to rethink their fundamental assumptions about how space, time, and energy work on the grandest scales. The Cosmic Horizon Paradox presents one of the most intriguing and puzzling challenges in cosmology. The universe is approximately 13.8 billion years old, which means that light from objects more than 13.8 billion light-years away has not had enough time to reach us. Based on the assumption that the speed of light is the ultimate speed limit in the universe. However, despite this limitation, we observe regions of the universe that are so far apart, sometimes vastly beyond the reach of light from the other region, that they could never have interacted with each other. This presents a paradox. How could distant regions of space end up with the same temperature and similar properties when they had no way to exchange energy or information? This paradox is especially evident when we consider the cosmic microwave background radiation, CMB, which is the faint glow left over from the Big Bang. The CMB is a snapshot of the early universe, providing us with information about its state just 380,000 years after the Big Bang. What's remarkable about the CMB is that it is remarkably uniform across the sky, with only tiny fluctuations in temperature and density. For regions of space that are so far apart that they should not have been able to influence one another, this uniformity is puzzling. According to traditional cosmological models, distant regions of the universe would not have had enough time to interact and reach the same temperature or state. Under normal conditions, the temperature differences between distant regions of the universe should be far more pronounced, with large gradients of heat and cold. Instead, we observe a surprising uniformity. So, how could regions that are beyond each other's causal influence, meaning they could not have exchanged light or energy, end up in a nearly identical state? This conundrum led to the development of the theory of cosmic inflation, a groundbreaking idea proposed in the 1980s by physicist Alan Guth. The theory suggests that, just after the Big Bang, the universe underwent an incredibly rapid and exponential expansion. During this brief period, lasting a fraction of a second, the universe expanded by an enormous factor, much faster than the speed of light. The expansion was so extreme that regions of space that were previously causally disconnected, meaning they could not communicate or influence one another, became part of the same expanding space. As a result, these regions were able to come into contact, exchange energy, and equilibrate in temperature, setting the stage for the uniformity observed in the CMB. Cosmic inflation solves the Cosmic Horizon Paradox, by allowing distant parts of the universe to have interacted in the very early moments after the Big Bang, before the universe expanded so rapidly that those regions could no longer influence one another. According to this model, the universe went from being extremely small to incomprehensibly vast in an infinitesimally short period of time, stretching regions of space that were once very close together and bringing them into thermal equilibrium. The inflationary period essentially smoothed out the universe, ensuring that distant regions shared a similar temperature and density, which we observe today in the CMB. However, the specifics of how inflation works, what triggered it, and what ultimately caused it to stop, remain areas of active research. The details of inflation are still not fully understood, and while the theory has successfully explained many of the universe's features, there are still questions about what the driving force behind inflation was, and how it fits within the broader framework of physics. One of the key insights provided by inflation is the flatness problem, which refers to the observation that the geometry of the universe appears to be nearly perfectly flat. Without inflation, the universe should have evolved in such a way that small deviations in curvature would have grown over time. But inflation explains why the universe is so flat, because the rapid expansion stretched out any initial curvature to the point where the observable universe appears to have no detectable curvature. Despite its success in explaining the uniformity of the universe, inflation raises its own set of challenges. For instance, inflationary theory predicts the existence of quantum fluctuations in the very early universe, which should have left tiny imprints on the CMB that could be detected. These fluctuations are thought to be the seeds of the large-scale structure we see in the universe today. Galaxies, clusters, and superclusters formed from these quantum fluctuations. Observations of these fluctuations have been made by telescopes like WMAP and Planck, which have provided compelling evidence for the theory. However, the exact mechanism behind inflation remains speculative, and some physicists are exploring alternative models of the universe's early evolution. Another important implication of the cosmic horizon paradox is that it forces us to reconsider the limits of causality. The theory of inflation suggests that the universe's rapid expansion allowed distant regions to become causally connected. But this idea also raises the question of whether the expansion itself broke traditional causality. If space can expand faster than the speed of light, what does this mean for our understanding of information and signals traveling across space? Could this imply that some events in the universe could occur in ways that we are unable to directly observe or predict? These are the kinds of questions that continue to drive cosmologists and physicists to refine their models of the universe's birth and evolution. In conclusion, the cosmic horizon paradox points to one of the deepest mysteries in cosmology: the apparent uniformity of the universe, despite regions being causally disconnected. The theory of cosmic inflation provides a compelling solution, offering an explanation for why distant regions of the universe appear to share similar properties, despite being far too far apart to have interacted in any meaningful way under normal circumstances. As our understanding of inflation and the early universe continues to evolve, the paradox serves as a reminder of the extraordinary complexity and beauty of the cosmos, and of how much still remains to be discovered about the origin and structure of the universe.